So the previous talks that we've sort of heard about from Dr. Lisa to Luke has set the stage nicely for thinking about AI and machine learning in sort of a scientific context. And so for this talk, I'll focus on some of the common pitfalls. And fortunately, most of these common pitfalls were mentioned by both Javier and Luke. So this will be sort of a quick recap, just to re-emphasize these pitfalls and also sort of re-emphasize the best practices that were mentioned that we can sort of adopt to avoid these common pitfalls. And so let's start perhaps with sort of the most fundamental pitfall, which is building a model without first aligning it with the scientific question. And this happens often. This is very common in research where people pick a method because it's flashy or it's because it's what they know to do, right? And so just like I think Luke emphasized, if you are not a domain expert, then it's important to engage with domain experts to first understand the question and then the underlying scientific objectives, and also understand whether the research question can be translated into what I call statistical hypothesis. And so once you've understood the research objectives, then you can then ask yourself whether the research question can even be answered with data. If the answer is no, then it means that the questions needs to be rephrased, right? If the answer is yes, then it means the next question is what kind of data are needed to answer the research questions? Are the variables in the data, the response variables, are they continuous or categorical, right? Are there any practical or scientific constraints that you must also consider? And we've heard about different kinds of models here, right? So does the question sort of allow for a black box deep learning model? Or is the question asking for a more interpretable sort of transparent model, right? So the answers to these and questions and other similar questions should then guide the type of model that sort of you choose. So I have some quick three examples here where the model execution sort of misaligned with the scientific and then practical reality. In the first case, the model predicted nitrate concentrations far beyond the measurable range of the instrument, making the model prediction or output practically sort of infeasible. And this is a common mistake. And when where model outputs are not constrained by scientific, practical, or resource realities. So ensuring that that alignment is there, sort of aligning what we can do resource-wise and what your model predictions say is very, very, very important, right? In the second example, the model sort of strategy, and I think Luke also talked about this, prioritize overall accuracy. And this is very common. So in doing so, you completely sort of mix identifying the high risk site that is the focus of this research question here. And so in those instances, make sure you really understand the research question. Is there a way to weight certain metrics more than the others? So in this case, weighting the recall on the high risk site rather than the accuracy will fix this problem. And then in the third example, the model attempted to predict absolute enzyme abundances from mass spectrometry data. And I might say when I started working with biological data, I also made these mistakes. So they are very easy to make. even though we know that only relative abundances are meaningful and they're measurable in this context. So overall, your data needs, along with practical and resource constraints, should drive the type of model that you choose, not the sort of the other way around. Again, we've heard a lot about this also, and this is also another common pitfall that people make, that is collecting data that does not represent the population that we care about. And best practices here include following good experimental design principles, so using random selection, randomization, and other good principles that will ensure that the sample that you take is as representative of the population that you want to study. I think a caution here that I want to emphasize here is that random selection doesn't always mean that you are getting a representative sample. I think let me go to the next slide to sort of highlight that. And this is very important, that random selection doesn't always mean that you are dealing with, you get a representative sample. There are times where you must think about the characteristics of your population. If your population is uniform, then random sampling may work and you may end up with a representative sample. If your population is heterogeneous, if there are items in your population, for example, that are difficult to sample, if there are areas that are difficult to get access to, then you must think about other strategies aside from random sampling, such as stratified random sampling, where you can sort of partition your population into groups and then intentionally sample from all groups. You can even, at times, in my experience, you can even use convenience sampling. There's nothing wrong with combining convenience sampling with random sample if it means your whole sample is representative, where for the higher risk areas, you can intentionally sample from those areas and then combine them with your random sample. So the takeaway point here is that if your data do not reflect your population of interest, then you cannot apply your result beyond your sample. So it's worth putting a lot of thought into the characteristics of your population and then how you then sample from that population. Let's jump to the next pitfall here. Again, this has been mentioned several times here, so we are like beating a dead horse here, but it's very important. So I want to sort of briefly also mention it, getting the sample size right. And generally, I think sample size, the performance of most of the models that we've heard about, both deep learning, most of the deep learning require a lot of sample sizes. Most of the interpretable models generally increase as your sample size increase. So that is why it's important to plan ahead and know the type of model that you want to run. Always, I advise people to use a power calculation, and power is our ability to detect differences that are there. And so we can use power calculations to figure out how many samples that we actually need for a particular model. If you can't collect those enough samples, there are Bayesian methods that have also been mentioned, where you can combine your limited sample with prior information or prior knowledge to get to where you want to get to. There are also currently transfer learning, hot shot learning methods there that you can borrow insights from a similar system to make up for your smaller data size. what I want to also sort of emphasize here is sort of the trade-off between resources that we live in a real world, right? So we don't have unlimited resources. And so before you begin your modeling and everything you do, the first question is how many samples can I even afford, right? If you can't afford those samples, then it might be better to at times reduce your scope. That is maybe reduce the number of experimental conditions that you are thinking about sort of considering. And there may be at times that you might be better for you to even rephrase your research question so that you can do a more efficient sort of statistical analysis. And then I also want to emphasize this thing here that at times more samples does not translate into sort of better sort of outcome, especially in the face of sort of resource constraints. And so what I have here is an example where this heat map is showing a power analysis for two phenotype 1 and phenotype 2. And so for sample size 7 for phenotype 1 and sample size, I think 8 for phenotype 2, you get a power of 80%. That is, you have an 80% chance of detecting any differences between phenotype 1 and 2. But then if you increase the sample size for phenotype 2 to 10, that power goes up to 82%. And so the question you ask yourself here is that, is it worth increasing the sample size to 10 if it means just a 2% increment in power? And the answer to this question will depend on how expensive those samples are. So expensive in terms of both, it can be cost, it can be money, it can be time, right? How expensive those three samples are. If those three samples are expensive, then in this case, it will not be worth it sort of going to 10 samples. If those samples are easy to come by, then it may be worth sort of going to 10 samples. And so power analysis is very, very important, right? It helps us sort of strike the right balance between statistical power and then available resources so that we can make smart and efficient decisions in our studies. The second pitfall, again, mentioned by previous speakers, so I'll quickly go over this, is also missing data. And we've heard that missing data sort of undermines the quality and credibility of our machine learning models, especially if they are not handled properly. They can introduce bias, they can reduce the model performance, and even at times obscure sort of meaningful patterns that we want to get. And so a common mistake is that people make is dropping all the missing values from our data. And if you do so, this can bias our result unless the data are sort of missing completely at random, which is very, very rare. And so the first step in understanding how we deal with missing data is understanding why the data is missing, right? Are they missing completely at random? Are they missing at random, or are they missing not at random? So, like I said, it's only when data are missing completely at random where that is where doing analysis on the complete data case may yield an unbiased result. In most other situations, we will need to use imputation methods or Bayesian models that can handle these missingness by design. So in conclude, I will ask all of us to check the PMAT package if you've not come across it before. It has various sort of imputation methods for handling missingness in omics data. Yeah. Again, we've also heard about batch effect. It's also another sort of common issue. So I want to sort of re-emphasize it that we need to be aware of batch effect and then account for it in our studies. So we've heard that batch effect happen when differences are driven by how the samples are sort of processed in batches rather than the actual biological or scientific signal that we care about. And so if we don't correct for these batch effects, our models may pick up these artificial differences, which can then lead to sort of wrong conclusions. And so always, if we are aware of the batch labels, then we should be correcting for the batch effect in our analysis. Or if you are aware of the batch labels, you can also include these batches as explanatory variables in our models. And the best way to avoid batch effect is to follow good experimental design principles. So we can randomize these batches as much as possible so that our data become less prone to these kind of biases in the first place. And so again, the multi-back package in R is also a good resource. It offers tools for doing batch correction in multi-omics data sets. Oh, good. Yes. The next pitfall is data leakage. And we've also heard about this also. So data leakage happens when information that wouldn't be available at prediction time sneaks into our model training. So like future data or labels. And so this can make our models seem much more accurate than it really is. And then it can then fail badly when we apply them in the real world. And so there are two common types of data leakages to watch out. One is the time-based leakage and then the target-based leakage. Time-based leakage happens when our model accidentally sees data from the future. So for example, using tomorrow's measurement to predict today's outcome. This is easy to miss if, for example, if we shuffle our time series data without keeping the time order, for instance. And so it's important to sort of make sure that we are keeping a record of all the sort of pre-processing things that we do, not to sort of mix the tomorrow's labels with today's label. Another form of leakage is the target-based leakage, and this happens when we include information in our features that is derived from the target variable. So an example is computing an average that already incorporates the outcome that we want to predict. And so I think Luke also spoke about this one, but to prevent data leakage, we always have to split our data into training, validation, and test set before we even start feature engineering. We avoid letting our feature or target information influence our feature engineering. Also use pipelines and workflows to enforce this separation. And then we should always be auditing our processes for both time-based and then target-based data leakage before deploying our models. I think we've heard a lot about overfitting, and so I'll be brief here. Overfitting is another classic mistake where the model performs well in the training set because, like it has been said here, because it memorizes all the little details and noise in your data, but then it fails to perform when you give it new or unseen data. And so one of the ways to avoid this is sort of making sure there are no data leakages, like we talk about, also using cross-validation techniques to test how your model performs on different subset of your data, and also applying different regularization techniques to keep your model from becoming complex. I think it has been, Luke emphasized this point, and I also want to say that if in doubt, the simpler model is always the best. If we can use the simpler model is often more robust and easier to interpret. And then the key thing to sort of note here is always compare our training error, and then our test error. If the training error is much more lower than the test error, then that is a sign of overfitting, and that means we should be sort of simplifying our model as much as possible. The next pitfall here is making sure that we don't use the wrong evaluation metrics. And again, this has been emphasized here, so this will be a quick one, right? And a common example that I think Luke also used in his talk is that using accuracy alone on an imbalanced data might make your model look great, but then you might actually miss most of the important cases, right? So instead of just randomly picking a metric, use a metric that match the nature of your data and your goals, right? So for example, use F1 scores when we are working with imbalanced data classes. F1 scores of one of our MCC, mythic correlation coefficient. When we are dealing with imbalanced data classes, use RMSE for continuous outcomes. And it's also a good practice. I saw this discussion in the Discord channel to always report more than one metric, right? So if you are dealing with sort of categorical data, then things like accuracy, precision, and recall will give your users sort of the full picture, and also include some measures of uncertainty if possible. So confidence intervals or standard deviations also will sort of complement the message that you want to sort of put across. And then, if possible, also show your result visually. So use tools like ROC curves and then confusion metrics to also sort of put your point across. So the key here is to choose and communicate metrics that actually reflect what success look like in your specific sort of problem, so that you will not be either underselling or overselling the analysis that you've done. Again, another pitfall is ignoring interpretability, and this has also been talked about. And we've seen sort of black box models that seem sort of powerful, but then they are impossible to sort of explain. And so, like I think other previous speakers said, in our scientific and applied work, interpretability is often just as important as performance. So if people can't understand your model, how your model is making decisions, they may not be able to trust it or even use it effectively. And so when possible, prefer simpler, more transparent models, and always tailor our explanation to our audience, right? So what makes sense, for example, for a technical audience might confuse a non-technical one. And so, and for complex models, this was also mentioned, don't forget to use tools like Sharp, ICE plot to help us sort of uncover and communicate how our model is making decisions to our audience. So interpretability is one important thing that we should be sort of focusing on. So if possible, use all the tools available to make sure that we communicate the way our models are making a decision to our audience. The next one, which has also been talked about here, is also reproducibility. So I'll quickly sort of go over this also. So reproducibility is the foundation of trust and progress in science. So without it, results cannot be sort of verified or built upon, and our time and effort will be wasted. And so Luke had a very great table of how to make sure that your work is reproducible. So use version controls like Git, DVC, and then ML flow, for example, to track changes. Always try to automate our workflows with tools like SnakeMake or Airflow to minimize human error. And we always also try and document your code, your key decisions, and any random seeds that you are using so that your future self and anybody who comes and use your work can follow what you did. And then finally, we can also share our code and data openly when possible using platforms like GitHub, Zenodo, and Figshare. I think one statement that I always keep with me is that if it is not reproducible, then it did not happen. And so we must make sure that our work that we are doing is as reproducible as possible so that we do not waste our time and effort. And so to wrap up this talk, uh, here are some sort of guiding principles to build machine learning models and AI models that last. We always should start with the right problem, not just the flashiest model. We should make sure that our data are representative and our sample size is appropriate. And we've talked about this quite a lot. Also choose the right evaluation metrics that match your scientific goals. Reproducibility isn't optional. It should build trust and ensure progress, scientific progress. And then we should endeavor to work closely with domain experts because their knowledge is invaluable. And then finally, when in doubt, we should always simplify, document, and then verify. So these habits will save us and our collaborators a lot of time and then frustration and down the road. Thank you for your time. I hope sort of these examples help us avoid some of these common pitfalls so that we build more robust, meaningful machine learning models in our research. Happy to take any questions.
So we have time for one or two questions before we conclude today's morning sessions.
Hi there. Where do you recommend documenting the decisions that you make as you're making them essentially? Because sometimes I find myself making a decision that I think will be relevant later, but it's not like, I don't know. I don't have like a system of storing those things except in my, GitHub or something like that. So I'm curious what you recommend.
Yeah, that's a great question. Thank you. It depends on what you are doing. What I try to do, for instance, is that if I'm coding, if, for example, if it is a coding work that you are doing, and you are using tools like RStudio or Jupyter Notebook or whatever, I try to write everything that I'm doing and every decision that I'm making in addition to the actual coding that I'm doing, right? So that I try to explain why maybe I'm using this function instead of this function, why I maybe treated the data this way instead of that way, so that if anyone who comes and use the code will be able to understand the decision that I make. And so I think it generally depends on what you're doing, but whatever you are doing now, I think my advice would be that you make sure that you document all the sort of the small decisions that you make in the places where you are executing the work. And so if it is an R Markdown, you make sure you use R Markdown, you document all your decisions there. If it is a Jupyter notebook, you make sure that you document all the decisions there.
Thank you.
I mean, just to follow up with what she asked about the question, do you mean like maybe if you are working in a particular environment, like commenting out maybe your code or like writing a summary of that, or maybe you have a separate document where you can always refer to, in guiding your decisions that you make or some kind of functions, because I believe that sometimes we want to keep things very simple. So there should be kind of a simpler way of doing that as well. So
Yeah, I think you've said what I had in mind. Yeah, if it is a code thing that you are doing, yeah, making use of the comment option, like I said, is very important. If it is a group work that you are doing, right, you can have a shared file where each of you can then document the decisions that you are doing in a file. I have found that to be very, very sort of useful in case you are not the only one even working on the project. So it will depend on what you are doing. But as you are data scientists, we typically work with the coding and then the modeling aspect. So in that aspect, making use of the comment option is very important. Commenting and then sort of writing down the decisions that you made in terms of how you're executing the model is very important. If it is not coding and it is sort of a shared group work, even thinking about the research questions, documenting everything in a shared file that everybody can follow is also very important. Yeah. So yeah, it's exactly the sort of thing that you said.